we're going to look at something called a standing wave. So the first thing I want to look at here is what happens when a wave is generated. So if a wave is generated, it's going to travel down, bounce, and come back the other direction. If there is a boundary to where this wave can go, it's going to bounce off and go the opposite direction. And when those two waves going opposite directions encounter each other, they're going to either add together or cancel each other out. So we're going to see a couple of examples here. So notice here, when the two peaks coincide, they add together and make the wave higher. When the two troughs, when the high and the low points coincide with each other, the waves cancel each other out. Okay, so I have kind of a version here. So here the waves are canceling each other out. Here they're adding together. So the two peaks add together, make a higher wave. Here they cancel each other out. Now let's imagine that we kind of give this a little shake and it creates a wave. Well, this wave kind of travels down the string, okay, hits the other side, and then when it hits the other side, it actually flips over and bounces back going the other direction. All right, so let's see how that looks in our animation. Okay, so if we go on, if we look at two sound waves that are traveling in the opposite direction, there we go. All right, so here's a wave traveling one direction, here's a wave traveling the other direction, and as they travel in opposite directions, we see it creates what's called a standing wave pattern, where it just fluctuates up and down depending on whether these two waves are increasing each other or canceling each other out. Okay, it creates a standing wave pattern like that. Now, if the wave pattern travels along and happens to hit exactly on the sinusoidal axis when it gets to its boundary line, then it's going to flip upside down and it's going to create what's called a standing wave like that. And that can happen whether or not, it can happen if there is several cycles or just one big cycle, but sometimes it doesn't hit exactly at an endpoint. So maybe it hits and it's kind of like this, and the endpoint doesn't match, so when it bounces off, it's kind of going like this and then like this, and so those don't make a standing wave. All right, and only make a standing wave if when it hits the endpoint, it matches with a point on the sinusoidal axis of the wave. So what we're going to see in this video here, this next video, is we're going to see a string tied between two, it's tied at both ends, and a frequency is going to be generated vibrating this string, and we're going to see that at certain frequencies it's going to vibrate at in certain standing wave patterns. Is it not going to full screen? There we go. Okay, so we see a 13.7 frequency, 27.4 frequency, 41.4. So 13.7, we're going to double that. It's going to be 27.4. So now we see two standing waves. Now it's tripling it. We see 3 standing waves. Now the frequency is going to be 4 times bigger. We see 4 standing waves. Now it's 5 times the original frequency, 1, 2, 3, 4, 5 standing waves, and now finally they're real hard to see, 1, 2, 3, 4, 5, 6 standing waves. Okay, so it turns out that that we can create standing waves that are based on frequencies that are multiples of each other. So if you have something, if you understand music, you might understand the term harmonics or overtones. When you play a musical instrument or when you sing, and there's something vibrating, whether it is the string of an instrument, the column of air in a woodwind instrument, the skin of a drum, the wooden surface of a marimba, the metal surface of a xylophone, anything like that that's vibrating, it can only vibrate with certain frequencies. And it has to do with how long the surface is, how tight the surface is, how thick the surface is. So I'm going to kind of just read through this here. All other things being equal, thickness of the string, material used to make the string or instrument, etc., the length of the string or the air column determines the wavelength of the sound and thus the pitch of the note. For a stringed instrument, the ends of the string correspond to nodes or points on the sinusoidal axis. For wind instruments, the open ends of the column must correspond to maximum or minimum points of the sinusoid. And so if I want to change the wavelength, which changes the pitch of the sound, I have to shorten the string by using the frets on a guitar. I have to shorten the air column by closing up holes on a clarinet, or maybe lengthening a column of air by extending a slide on a trombone. I can also, when I can't actually change the physical length of something, I can also change the rate of vibration by tightening or loosening a string or tightening or loosening a drum head. So you'll notice that, for example, if you see a xylophone has smaller and larger vibrating pieces of metal, or in a case of a marimba, wood, and they're loosely attached with little screws here so that they can vibrate and you strike them. And these are going to be the low notes because they can vibrate with longer frequency wavelengths, so they create low notes. These are going to vibrate, these have to have short frequency wavelengths because the ends of the wavelengths have to correspond to the length of the bar. Okay, so there's actually a great deal of engineering that goes into making musical instruments. The material used and what its natural frequency of vibration is, the length of the instruments. You've probably all seen pipe organs and seen how long, it has little tiny tubes that the air comes in that make the high notes, and great big long thick ones that make the low notes. So this whole thing about instruments is all based on lengths of waves of sinusoidal functions, because that is what sound is based on. So if you are into music, there is quite a lot of mathematics in music.